Hey everyone, this tutorial is going to be on the molecules module. We're going to start with a little bit of review just to make sure everyone is on the same page. I'm not going to go over everything on this page because, again, this should just be review. We're just going to briefly go over Lewis theory and bonding. So, Lewis theory states that the bonding capacity of an atom is dependent on its valence electrons. When electrons are transferred, an ionic bond is formed. When electrons are shared, that's a covalent bond. The goal is to end with an octet. Polar covalent bonds are when electrons are not shared equally. This can be seen on the electrostatic potential map. You'll see a buildup of electrons on the Cl side, and then a deficiency on the hydrogen side. Electronegativity relates to an atom's ability to attract electrons. So, the electronegativity value of a bond shows you if it's covalent, polar covalent, or ionic, based on how much an atom is attracting electrons in the bond. When drawing a molecule and figuring out its structure and bonding, it's important that the formal charges are kept as low as possible. Negative charges should be on higher electronegative atoms, and formal charges of the same sign on adjacent atoms is unlikely. Formal charge can be calculated by taking the valence electrons of an atom, then subtracting the bonds plus the dots being each electron in a lone pair. According to VSEPR theory, electron pairs will repel each other, so a molecule's shape is formed to minimize this repulsion. Here is a chart of the geometry made from the different number of electron groups in a molecule. 2 electron groups in a molecule means that the geometry will be linear, giving it a 180-degree bond angle. 3 electron groups gives us the trigonal planar shape with a 120-degree bond angle. 4 electron groups gives us the tetrahedral shape with a 109.5-degree angle. 5 electron groups is the trigonal bipyramidal, which gives us a 90-degree bond angle and a 120 bond angle between those 2 electron groups and then those 3 electron groups. 6 electron groups gives us the octahedral shape, which will have all around 90-degree bond angles. The octet rule that I mentioned earlier doesn't always apply. Central atoms are capable of forming up to 6 bonds in the octahedral shape. This is possible through hybridization. Hybridization also explains atoms like carbon having a bonding capacity of 4, even though it has a pair of electrons in its 2s orbital and 2 in its 2p orbital. One of the paired electrons in the s orbital can be promoted to the p orbital, and the shell that forms is known as the sp3, since it's made of 1 s orbital and 3 p orbitals. This explains our diagram of electron geometry from earlier. This is where we're going to go into more detail and do some problems. This hybridization concept is called valence bond theory. It allows us to understand the 3D geometry of a molecule. That gives us valuable information about the molecule itself. Its polarity is dependent on its shape. Symmetrical molecules will not be polar even if its bonds are polar covalent. An asymmetrical molecule will be polar if it has polar covalent bonding. Water arguably is the most important molecule in the universe, and it gets its properties from its bent molecular shape, made possible through hybridization. For further enrichment, we're going to talk about energy levels of orbitals. The different orbitals all exist on different energy levels. So, when a carbon 2s electron gets promoted to the 2p orbital, the orbitals merge and end up on an intermediate energy level. Each of these new orbitals are individually called sp3 orbitals. People make that mistake a lot as one p orbital has 2 lobes, but each lobe is an independent sp3 orbital. Like I said earlier, molecular geometry is a chemist's greatest tool for predicting properties of a molecule or predicting reactions. If we go back to an earlier module, you'll remember we talked about conformers, molecules with the same arrangement but different rotation of atoms. This is possible due to hybridization. If you were to have 2 carbons and 6 hydrogens bond together, you'd make ethane. If we look back at carbon forming sp3 bonds, it creates a tetrahedral shape with bond angles of 109.5 degrees between all the electron groups. The carbons that are bonded together are able to rotate because of this structure. The hydrogen 1s orbitals across from each other will not touch each other, so the carbon is able to rotate. The hydrogens themselves cannot move due to the fact that they are interacting with neighboring hydrogen 1s orbitals. Hybridization theory was able to predict and explain topics from several modules back. Once again, hybridization is clearly fundamental to all parts of chemistry. Hybridization can also help us understand cis and trans isomers. We were taught that double bonds were rigid, and therefore cis and trans isomers were not interchangeable, but we weren't totally explained why. Well, if we look at the hybridization of a carbon to form double bonds, we end up with a p orbital left over, along with 3 sp2 orbitals. One of the electrons from the s orbital is still promoted, but only one of the s orbitals and 2 of the p orbitals hybridize together, and the p orbital is left over. If we were to take a look at ethene, we could see the double bond in action. The double bond is formed by 2 sp2 orbitals coming together, but then also by the 2 p orbitals coming together. Those are called the pi bond. This whole region is one p orbital, even though it looks like 2 lobes. The pi bond part of a double bond is what causes the rigidity. When 2 p orbitals come together, they create an electron density that looks like this donut shape that you see. If this bond were to rotate, it would break. You can see that illustrated here due to their parallel nature. When they're rotated, you get that snapping. Hybridization can also help explain the bonding of alkenes, alkynes, and alkanes, something we haven't really explored yet in chemistry. Pi bonds are much weaker than sigma bonds due to the parallel overlap of p orbitals. They aren't as strong as the sigma bonds directly overlapping. We saw how the pi bonds broke earlier when we looked at cis and trans isomers. Pi bonds break more easily and therefore require less energy to break. This makes alkynes and alkenes more reactive than their alkane counterparts. When a pi bond and a triple or double bond breaks, the carbons will have either 1 or 2 extra bonding spaces. When something new bonds to these places, it's called an addition reaction. Now let's try an example and put it all together. We're going to look at propylene. We can see it has 3 carbons bonded to 6 hydrogens, and it's going to be 1 carbon-carbon double bond as it ends in -ene. This means that the carbons with a double bond have been hybridized to the sp2 orbitals, with 1 p orbital for the pi bond in the double bond. This means that the one on the end has room for 2 more hydrogens, and the one in the middle has room for 1. The carbon on the other end does not have a double bond, so it has been hybridized to the sp3 orbitals, allowing it 3 more spaces for 3 hydrogens. Just by looking at this atom, we can deduce its molecular shape, which gives us great insight to its properties and reactivity. We know that double bonds are rigid, as the pi bonds are parallel when overlapping, so this bond cannot rotate. We know that single bonds are not rigid, and the hydrogen groups are not interacting, so this bond is able to rotate. We also know that double bonds make for greater reactivity, as they can break and make room for another bond, so this molecule has potential for addition reactions. Finally, we can tell the whole 3D shape by knowing that sp3 orbitals will make tetrahedral shapes, and the sp2 bonds will make the trigonal planar shape. Thank you for listening. I hope I helped enrich and deepen your understanding of molecules, molecular shape, and hybridization. I hope you all now can appreciate the importance of hybridization and molecular shape in the rest of chemistry and how it influences everything we will talk about in the rest of our chemistry careers.